Now that we've gotten really good at counting different possibilities and outcomes that could come up out of an event, we're ready to actually start calculating some probabilities. And so that's what we're going to look at today, is an introduction to probability. And probability starts out with making sure we know how to clearly define what is called the sample space. And the sample space is the set of all possible outcomes. Set of all possible outcomes of an experiment. So, for example, if a card is drawn from a deck, standard 52 card deck is what we'll always work with, and the suit is recorded. So this is an experiment to find the suit. The sample space of this is we could get a heart, we could get a diamond, we could get a club, or we could get a spade. This is the sample space, the set of all possible outcomes when I draw a card from a standard 52 card deck and record the suit. Now, sometimes it's not as straightforward as just listing the possibilities. Let's say a family has 3 children. And for the sake of simplicity, we're going to just look at whether or not they have a boy or a girl. Well, the first child could either be a boy or a girl, right? We'll use B for boy. The second child then could be a boy or a girl. Dropping my letters here. And it doesn't matter which case we have. If the girl came first, the second child could be a boy or a girl. And then you could see how this pattern will continue, that you could get a boy or a girl for the third child, regardless of what happened for the first child, boy or girl, regardless of what happened for the second child also, boy or girl, boy or girl. So what we can do now is follow down all these branches of this tree diagram. That's what this is called, by the way, a tree diagram. Uses a branch for every possibility. Following down the branches, we can see what type of children we have. With 3 kids, you could have a boy, a boy, a boy, a boy, a boy, a girl, a boy, a girl, a boy. Following the next branch, a boy, a girl, or a girl, boy, boy, or a girl, boy, girl, or a girl, girl, boy, or a girl, girl, girl. And so now, this set is the sample space of the possible family outcomes of this family with 3 children. So sometimes when it gets a little more involved, we'll use a little tree diagram like this to find all the possibilities, and then later we're going to use tree diagrams to help us actually calculate some probabilities. Once we know how to find the sample space, all possible outcomes, we're ready to start talking about the idea of calculating probabilities. A probability is simply a chance that an event will occur. And we represent that chance with a number between 0 and 1. Closer to 0 means it's unlikely to happen. Closer to 1 means it's more likely to happen. And if it's right in the middle at 0.5, we say it's equally likely to happen or not happen. So, for example, if a family has 3 children, referring to the example up above, that tree diagram, we're going to find the probability that they have 2 girls. And often you'll see probabilities written in this form where we have a P and then in parentheses something. That means we're asking the probability that this thing occurs. The probability that we have 2 girls. Well, if we look at that tree diagram that we just made, we see that there are 2 girls on a couple of the options. 1, 2, 3 of the options have 2 girls. And so the way we calculate that probability is we take the number of desirable outcomes, there are 3, divided by the number of possible outcomes, or divided by the number of things in the sample space. If we count our sample space, there's 1, 2, 3, 4, 5, 6, 7, 8 things in the sample space. So the probability of getting 3 girls is going to be the probability of getting 2 girls is 3/8. Now, probability can be either expressed as a fraction, a percent, or a decimal. Our textbook seems to prefer fractions. I think fractions are very misleading because it's hard to compare fractions to each other. If we're comparing 700 out of 2,500 and 600 out of 2,100, which one's bigger, that's really hard to tell in fraction form. So I'm going to prefer, for our class, we will always use decimals. And if we have to round the decimal, we will round it to 4 decimal places. So 4 decimal places is going to be the standard for probability in this class. I do not want fractions. I do not want percents. This one, we don't have to do any rounding. It's 0.375. Makes it really easy to see how close to 0, how close to 1, where we're at. There's a 0.375 probability that this family will have 3 children, that this family of 3 children will have 2 girls. Let's do another simple probability problem. Let's say a jar contains 4 red marbles, 3 blue marbles, 2 white marbles, and 1 green marble. We're going to start with finding the probability that I draw a marble and get a red or white marble. Well, we see there are 4 red and 2 whites. So the number of desirable outcomes, there's 6 of them, divided by the total number of outcomes there are. 4 plus 3 plus 2 plus 1, there are 10 marbles to choose from. So 6 divided by 10 is going to be 0.6, is the probability that I get red or white. How about this probability? What's the probability I draw a marble and I not get a blue? Well, how many non-blues are there? 4, 2, and 1. There are 7 non-blues out of the 10 marbles. So the probability I draw a non-blue is 0.7. That's basic probability. You've probably seen this before, no pun intended. So we're going to try and make our probability problems for this course a little more interesting than just 6 out of 10. To do that, we have to set up a little bit of vocabulary. First, we're going to talk about this thing called mutually exclusive events. 2 things are mutually exclusive when they both cannot happen at the same time. An example of mutually exclusive. Well, let's do some. Let's look and see if these things seem like they are mutually exclusive. Let's say you draw a card from a deck, and I want to know, is it a face card and an ace? Can it be both? Can you be a face card and an ace? You could be a face card, that's Jack, Queen, and King, or you could be an ace, but there's no way to be both a face card and an ace. So, is it a face card and an ace? No, it can't be, because these two things are mutually exclusive. You can't have both at the same time. How about this? Similar problem. Let's say you draw a card from a deck, and I want to know, is it a face card and a heart? Well, it could be, because you could have, for example, the Queen of Hearts. That is a face card and a heart. So these two options are not mutually exclusive. So we'll say yes, you could have the Queen of Hearts, therefore they are not mutually exclusive. So that's what we mean by mutually exclusive. They cannot both happen. It cannot be 100 degrees outside and snowing, because to snow it has to be around 30 degrees. It does not work. This is going to help us set up what is called the addition rule. So let's say, keeping on this theme, we draw a card from a deck. We want to know the probability that it is a number or a club. Now, by number, we mean the numbers 2 through 10. The ace, Jack, Queen, King are not technically numbers. So there's 2 through 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 9 numbers. In 4 suits, so 9 times 4, there are 36 total. So there are 36 out of the 52 cards are numbers. What about clubs? Well, clubs, there are 13 clubs in a deck out of 52. There's 13 of each suit. Well, if I want to get the total here that we have, we would, it would seem, add these fractions together. 36 out of 52 plus 13 out of 52. But the problem is a couple of cards have been counted twice. Notice number and club are not mutually exclusive. There are some numbers that are clubs. Those cards have been counted in both groups. For example, the 2 of clubs, the 3 of clubs. These have been counted both as numbers and clubs. So we have to get rid of the double count, similar to what we did with the Venn diagram. To find what the missing part, we had to subtract what we already knew. Subtract out the double counted. How many are in the number club group? Well, it's the numbers 2 through 10. There are 9 numbers. There are 9 repeated cards out of the 52. So we can just do this arithmetic here, probably on the calculator. 36 out of 52 plus 13 out of 52 minus 9 out of 52. And when we round that decimal to 4 places, you get 0.7692. The probability of getting a number or a club is 0.7692. And I want to kind of formalize what we just did there with the addition rule, where we take the probability of getting A or B. Notice union is the word or. We talked about that when we had union with sets. Union comes up with or. The way we get that is we take the probability of A, add the probability of B, and then we had to subtract the double counted probability. And that's the probability of both. The probability of A and B. And that intersection, you remember from sets a couple days ago, is associated with the word and. This is an important probability formula that we're going to be using. The probability of A or B is the probability of A plus the probability of B minus the probability of both. So, if we roll a die, typical 6-sided die, what is the probability that it is even or less than 5? Well, we'll add the individual probabilities and subtract the probability of both. The probability that it is even, there are 3 even numbers out of the 6. Plus, the probability is less than 5. That would be 1, 2, 3, 4. There are 4 out of 6 numbers that are less than 5. But we have to make sure we subtract off the repeat. Both of them. The even numbers less than 5. 2 and 4. There are 2 numbers that are even and less than 5 out of 6. And so when we do this on the calculator, 3/6 plus 4/6 minus 2/6, we end up with a probability of 0.8333. How about this problem? Let's say the probability of sun tomorrow, maybe not tomorrow. We're still in the middle of winter, aren't we? The probability of sun, let's say, is 0.4 for a given day. The probability I go swimming on this day is 0.2. And the probability it is sunny and I go swimming is 0.1. What is the probability I go swimming or it is sunny? Well, we know from our formula that the probability that it is sunny or I go swimming is equal to the probability of sun plus the probability I swim minus the probability of both sun and swim. So the sun probability is 0.4 plus the swimming probability of 0.2 minus the both probability of 0.1. That is equal to 0.7. There's a 70% chance that I will go swimming or it will be sunny on this given day. How about this? The probability I read a book tonight is 0.35. The probability I watch TV tonight is 0.55. They are mutually exclusive. What is the probability I read a book or watch TV? Again, we see that keyword or, this or that, to find the probability that I read or watch is equal to the probability that I read plus the probability that I watch minus the probability that I do both read and watch. And we're given a lot of this information. The probability that I read a book is 0.35. Plus the probability I watch TV is 0.55. Minus the probability I do both. Do they tell us both? Sort of. They tell us these are mutually exclusive. Mutually exclusive means there's no way I'm going to do both. I either have time to watch my TV program or I have time to read my book, but there's no way I'm going to be able to do both. Mutually exclusive means both the intersection is going to be 0. So, the probability that I read or watch a TV is 0.9. Adding together 0.35 plus 0.55. If they're mutually exclusive, we can just add the individual probabilities together. If they're not mutually exclusive, we have to subtract out the overlap where we get both of them. Another type of probability problem that we're going to work with after our addition rule are doing probabilities with tree diagrams. And as we do tree diagrams, we're often talking about multiple things happening, multiple probabilities and we know that by, we'll often use the word and. You could write down up above when we were doing the addition rule, we were talking about the word or. Either draw a number or draw a club. We weren't trying to draw both. We didn't care which. Multiple probabilities, we want and. We want them both to occur. When we want both to occur, multiple probabilities, we will multiply the individual probabilities. And tree diagrams are nice for this because we can multiply down the branches. Here's what I mean by that. Let's say 2 marbles are drawn from a can with 7 blue marbles and 3 red, without replacement. So I draw one out, and then I draw another one out. I now have 2 marbles in my hand. Red and blue. We can model this with a tree diagram. My first draw could be a blue marble, or my second draw could be a red marble. As I do this, the probability of getting a blue marble is 7 out of 10. 7 out of the 10 marbles are blue, and for the red, 3 out of the 10 marbles are red. Then I'm going to do a second draw where I could get a blue marble, or I could get a red marble. In fact, I could do it on both of these, getting a blue or a red marble. Give me a little more space here. Notice, though, in this first blue branch, on the top, I've already drawn a blue marble out, which means there are no longer 7 blue marbles left. There are only 6 blue marbles left. Out of, there were 10 total, but now there's only 9 left. Notice the probability has changed because I didn't put the marble back. The tree diagram helps us kind of follow that. With the red branch, just below it, we still have 3 red marbles left because we drew a blue one the first time. There's just 9 marbles left to choose from. Or, in the alternate reality, where I drew a red marble first, to get a blue marble second, there are 7 blue marbles left out of, because I've drawn 1 marble, there are now 9 left. Or I could draw a red marble. Because the first marble I drew was red, I now have 2 reds left to choose out of the 9. So there's 4 different possibilities that could happen. I could draw a blue, then a blue. I could draw a blue, then a red. I could draw a red, then a blue. Or I could draw a red, then a red. The way we calculate the probability for each is we're going to multiply down the branches. For the blue, we take 7/10 times 6/9. When we do that, we get, doing it on the calculator, 7/10 times 6/9 is 0.4667. Blue-red, the probability of a blue is 7/10. The probability of a red is 3/9. And when we do that on the calculator, we get 0.2333. Red-blue, that's 3/10 times 7/9 equals, again, 0.2333. And red is 3/10 times 2/9, which is 0.0667. And so now we could make any type of probability conclusion we had to from this. The probability of getting a blue is 0.46667. The probability of getting a blue-red is 0.2333. Also, the probability of getting a red-blue, ironically, is also 0.2333. And the probability of getting a red-red is 0.0667. What I like to do at this point is add these probabilities together because I want to make sure they add up to the total probability that something occurs. And we're guaranteed that if I draw 2 marbles out, I will get something. So if you add them all up, they should add up pretty darn close to 1. And they do. Sometimes with a round-off error you can be off by 1,000th or something, but in this case it all worked out just perfectly. So that's how we can use a tree diagram to help us calculate some probabilities. There's another way we can calculate probabilities as well. I think we're on letter F now. The last way we're going to look at today is using combinations to calculate probabilities. Let's say, taking a look at this similar problem, let's say a jar contains 4 red marbles, 2 blue marbles, 5 green marbles, and let's say 4 marbles are drawn without replacement. Let's see if we can find a few probabilities. Let's find the probability that we get 2 red marbles and 2 green marbles. Now, one thing I notice here is we again don't care about the order the marbles are drawn. I'm not asking for the probability of red, red, green, green. All I want is 2 reds and 2 greens in the final solution. I don't care what order. In that case, we can use a combination. But since we're talking about reds and greens, we need a combination for both situations. So we'll do a combination for the reds first. There are 4 reds to choose from, and we are going to select 2 of them. With the greens, there are 5 greens to choose from, and we're going to choose 2 of them. Multiplying those together will tell us the number of desirable outcomes there are. We simply need to divide this by the total number of possible outcomes. The total number of marbles we have are 4 plus 2 plus 5. There's 11 marbles we're choosing from, and we are drawing 4 marbles. So this is the same exact setup we saw with the basic probability. We're just using combinations to help us count the number of desirables and help us count the entire sample space. Bring the calculator to where we can see the problem. We're going to do 4 math over to probability and down to combination. 2 times 5 math over to probability down to combination. 2 divided by 11 math down to combination 4. Hit enter, and the probability that I get 2 green and 2 red is 0.1818. 0.1818. How about this problem? Let's find the probability that I get no reds. No reds. That means we're looking at the 2 blues and the 5 greens. There's a total of 7 marbles to choose from. And again, we are drawing 4 of them. Just looking at the non-reds for our numerator. Our denominator, still we look at everything, all 11 marbles, and we're still choosing 4. Again, we can use our calculator to find this probability. 7 math over to probability down to combination. 7 choose 4 divided by 11 math over to probability down to choose 4. The probability I get no reds is 0.1061 when I round it. 0.1061. How about we try one more of these? Let's find the probability that I get at least 1 green. Now that might be a little trickier. What that means is really the probability I get 1 green, or 2 greens, or 3 greens, or 4 greens. Now, fortunately, these are mutually exclusive. I can't draw a bunch of marbles and have 3 greens and 1 green. I either have 3 or I have 1, so we don't have to worry about double counting here. However, we would have to add each of these together. Calculate the 1 plus the probability of 2 plus the probability of 3 plus the probability of 4. But there is another option. We're going to calculate the complement. The probability that I do the opposite of this. The opposite of getting at least 1 green is the probability of getting no greens. Because this will make up our entire sample space. We either get no greens or we get at least 1 green. That means these two halves should add up to 1. Or better said, we're going to take 1 minus the probability of no greens, and that will tell me the probability that I get at least 1 green. In other words, we're subtracting out from 1 all the cases that don't work, and what's left is what does work. So let's do that. I lost the number of marbles we're working with. Here we go. Keep them on the screen. We've got 1 minus no greens. So the non-green marbles, that's the 4 red and the 2 blue, there's 6 to choose from. We're going to choose 4 of them. Over, we said there's 11 total marbles to choose from, and we're going to choose 4 of them. So on the calculator, 1 minus 6, math, over to probability, down to combination. Choose 4. Whoops, not 66. Delete one of those 6's. Divided by 11. Math, probability, down to combination. 11, choose 4. Enter. And we get 0.9545. 0.9545. The probability that I get at least 1 green, if I draw 4 of them, is a 95% probability. 0.9545. All right, enough with picking marbles out of jars. What we're really interested in is how I can get that winning poker hand. What is the probability that I get 2 pair in a poker hand? Poker hands are out of 5 cards. And 2 pair means I have a pair of 7s and a pair of 2s, or a pair of queens and a pair of kings. We can calculate this also with combinations. When we're looking at our poker hands, we need to make 2 choices, and sometimes those 2 choices have to be made several times. We have to choose a suit, and we have to choose a number. With 2 pair, we're most interested in the number, so we're going to do that first. Of the 13 numbers, combination, we're going to choose 2 of them to be pairs, because both of them are going to behave the exact same way. 2 cards and 2 cards. Now that we've done that, we're going to pick the suit. Let's say we've picked jacks. There are 4 jacks. We're going to choose 2 of them to be a pair. The other pair is queens. There are 4 queens. We're going to choose 2 of them to be queens. But that only will give us 4 cards in our hand. We need a 5th card. How many cards are left to be chosen from? Well, we don't want to get a repeat of a card we already have, because then I'd have a full house, 3 of a kind and a 2 of a kind. So this has to be a different number. Remember, there are 52 cards in a deck. We don't want one of the 4 jacks, and we don't want one of the 4 queens, because those are pairs already. So we have to subtract those out. There are 44 cards left. Of the 44 remaining cards, we want to choose one of them. Out of how many hands are possible? Well, there's 52 cards in a deck, and you choose 5 of them. This will give us the probability of the most basic winning hand possible in poker. Let's see what it will give us. 13, combination, 2, times 4, combination, 2, times 4, combination 2, times 44, combination 1, divided by all possible outcomes, 52, combination 5. The probability you get 2 pair, the most basic of poker hands, is 0.0475. 0.0475. Less than 5% of poker hands will come with a pair in them. That's going to wrap up our introductory look at probability. We're going to dive in really deep over the next couple days. I want to make sure you know what mutually exclusive is, how to use the addition rule when you want one probability or another probability, and how to multiply probabilities when we're ANDing, when we want A and B to occur. Multiply down the tree diagram, multiply probabilities for combinations. Take a look at the homework assignment tonight. Come to class with questions. We need to be probability masters before we get into some more interesting types of probability.